All right, number 11. An atomic nucleus initially moving at 420 meters per second emits an alpha particle in the direction of its velocity, and the remaining nucleus slows down to 350 meters per second. If the alpha particle has a mass of 4u and the original nucleus has a mass of 222u, what speed does the alpha particle have when it is emitted? So it seems like this problem involves a bunch of stuff we haven't learned. And it's true that we haven't talked about alpha decay. It's also true that we haven't specifically talked about the mass units of U, or unified atomic mass units. But you don't have to know any of that information to finish this problem. This problem is really just conservation of momentum. And to work it, you don't need any more knowledge than what we already have about momentum. So it's not a collision, really, which is what most momentum problems we worked were, but it's still, every physical process that has ever been observed follows the law of conservation of momentum, including alpha decay. So before the decay, or before the emission of the alpha particle, you have, if the particle, the mass is 40 and the original nucleus is a mass of 222u. All right, so the original nucleus has a mass of 222u, and its speed is 420 meters per second. So the momentum initially is 222 times 420. And the units here will be u times meters per second, which is not standard at all, but it's okay because later we're going to use conservation of momentum, and both sides of the equation are going to have units of u, and the units will cancel, and you'll end up with just meters per second to find the speed of the alpha particle. If that bothers you, there is a conversion in the data booklet to go from u to kilograms. So you could totally convert to kilograms and work this problem like you would normally work it in the units that you're more familiar with. But you don't have to do that. So 222 times 420 gives you 9.324 times 10 to the 4. So that's the momentum before the emission. The total momentum in a system before some event happens has to equal the total momentum in a system after that event happens. So sum of the initial momentums equals the sum of the final momentums. This is one way you can write down conservation of momentum. So this is the total momentum before. And it has to be equal to the total momentum afterwards. Well, after the emission, there's two things. And so the momentums of those things will be m1 times v1, let's say, plus m2 times v2. Let's say m1 is the new nucleus, and m2 is the alpha particle. We know the mass of the new nucleus will be the mass of the old nucleus minus the alpha particle. So I guess you need a slight understanding of alpha decay here. On the 1718 IB1 final exam, I will not give you a problem that requires you to know about alpha decay. But the mass of the new nucleus will be the mass of the old nucleus minus the mass of the alpha particle because it lost that. So that's 218u times whatever the speed of that nucleus will be. Oh wait, they give us that number. It's 350. So 350 meters per second is the speed of the new nucleus. The alpha particle has a mass of 4u, and we're solving for v2. That's what we're solving for. So do you see how every term has units of u times meters per second, units of u times meters per second, units of u, and then this will be meters per second. So since to solve for V2, we're going to end up dividing by 4u, that will cancel out the u's over here. This is why you don't have to convert to kilograms initially to work this problem. So if you solve for V2, you get 9.324 times 10 to the 4 minus 218 times 350, all that divided by 4, which will be 4.235 times 10 to the 3.